Hello, this is the first lecture on compliant mechanisms. The course title is Compliant Mechanisms, Principles and Design. In this lecture, we will have an overview of compliant mechanisms to see what they are, what the concept is and so forth. Let us begin by looking at a few compliant mechanisms that my group at Indian Institute of Science works on, has been working for several years. What you see here are compliant mechanisms at several sizes: macro, that is very large, and micro, that is very small, of the order of microns, as in microsystems or micro electromechanical systems. And then in between there is also meso, that is, let us say hundreds of microns to a few centimeters. That is what we can call it, a mesoscale between macro and micro. And then also the nanoscale, for which I have shown proteins which are also in a way compliant mechanisms that you will appreciate once we understand what they are. In this lecture, we will have an overview, and there is a subtitle to compliant mechanisms which it says is motion without hinges and sliders, and that summarizes what compliant mechanisms are. Without having joints such as hinges and sliders and other types, we can have mechanisms that do exactly the same thing as the conventional mechanisms would do. Let us look at a couple of conventional mechanisms. The one that you see here is has, okay, let me see, this one I have to get out of this arrow, yeah. So, if you turn something here circumferentially, it is moving radially in and out as this mechanism shows, and mechanisms intrinsically are very beautiful. As you can see here, one can have it on a circular window to open and close, or you can look at this Hoberman linkage, which again takes this outward motion over here to inward motion along the radial direction for these things. So, a circle grows bigger and smaller as you move, whereas here we are turning, right. You can see these circles moving like that. So, there is circumferential motion. These are all the mechanisms that have rigid bodies and joints. That is why we call them rigid body mechanisms. As opposed to that, you can have compliant mechanisms which are shown here. Whatever these two mechanisms do, they can do without having any joints. In fact, here there are a few joints, but they can also be removed if you were to use three-dimensional machining of this polypropylene device here. We will learn more about this in a case study much later in the course. So, you can have an equivalent compliant mechanism for any rigid body linkage that you come across. Let us look at this mobility that is attained because of elastic deformation, that is with compliant members as opposed to rigid members connected with joints, for which I have taken a day to day object, which is basically a can of a coffee powder here. There is a lid here for which there is a sketch, but what I will show first is the real one that I got here. So, you can understand what this is. So, this is a can with a lid, and okay, here is a can with a lid that can be screwed in and out, but if there is coffee powder in it, you want it to be fresh. So, it has to be a tightly sealed one. So, they have this mechanism. If you look at this, there is a hinge here with the white one, that is why I am able to rotate, and there is, with respect to this white one, this transparent one has another hinge. So, what we have here is a RR serial manipulator, but the moment I put it on top of it like this, I put it on top, now it actually becomes slider crank. If I hold it like this, when it is at top, it is like a slider crank, because there are two joints and a slider and a slight rotation also here, it is a slider crank. And once this thing touches this lip of the lid, then it cannot move anymore, it becomes a structure. That is, it cannot move anymore like a rigid body, but this particular thing can actually flex, that is elastically deform, so that it deforms and allows more rotation, and when I push further, it actually becomes bistable and it actually snaps. If I do it fast, you can hear the sound as well. So, this is a mechanism that has smooth transition from a rigid body serial chain to compliant mechanism. Let us now look at the sketches that we have in the slides. So, the first one shows that there are two bodies like this, these two. This is a serial chain, rigid serial chain, what we call RR chain, revolute chain. The moment it is placed on the top, as I showed, when I move this back and forth, this acts like a slider crank mechanism, which is a rigid closed chain. The moment it touches here, at this point it does not have any mobility, it just gets stuck and it cannot move further because this is obstructing it. But if you continue to turn this crank, then this black thing has to elastically deform, and then it can move, and in that process it achieves kind of a bistability by going and coming down to the perpendicular, holding it very tight. Okay. So, this becomes an elastic chain. We have rigid serial chain, rigid closed chain, and then an elastic chain, and that is how this particular mechanism works. In the same mechanism you have three different things: serial chain, closed chain, both are rigid, and then an elastic chain. But the crucial to this mechanism is this one, which is the elastic segment. So, this is the animation, we can just watch it, what I already showed with the real device. So, right now what you see is basically like a serial chain, there are two rotations there. The moment you place on top of that, that becomes a slider crank linkage, and then once you bring it far enough and it touches the lip on the can, it becomes a structure, cannot move, but you can still push it. At that point the transparent body will elastically deform and get this motion. So, we can look at mechanisms in general as rigid chains or elastic chains. Rigid chains will give us rigid body mechanisms, and the elastic chains will give us compliant mechanisms. This is the way we can compare and contrast traditional mechanisms without elastic deformation and those that are compliant mechanisms that have elastic deformation. Here we have kinematic pairs, which is the technical name for joints, or what we call kinematic joints. They are pairs because they connect a pair of bodies, and then those bodies are rigid bodies. So, every kinematic pair, for example, if there is a revolute joint in this robot manipulator, these two rigid bodies are connected by a revolute joint, and same thing here and so forth. Or you can also have parallel chains, parallel rigid chains, such as this revolute, spherical, cylindrical, and revolute RSCR, spatial linkage. It is a parallel mechanism, this is a serial mechanism, but both are chains of rigid bodies where individual bodies in that chain are connected with various kinematic pairs. As opposed to that, in compliant mechanisms, two examples are shown here. One of them is a forceps that I have a model here. So, in this forceps, if you see, okay, of course, this is the blue one. So, here if you look at this, it works like the normal forceps. If you put something here, you can pick it up, or if you have sharp edges, you can even use like a pair of scissors. But if you notice, this does not have any assembled rigid bodies. There are of course rigid segments, but it has this flexible joints, these four places, which gives this simple forceps the ability to work. So, let us go back to the slide now to look at what we can call discrete compliance, where there are these four flexible joints that give it the functionality that it has. As opposed to that, we can call them elastic pairs. This, just like we have kinematic pairs, we have elastic pairs here. As opposed to this, we have other kind of compliant mechanism. We will see a movie of it later in this lecture, which has distributed compliance. If this is discrete, that is, deformation is limited to a few locations. Here the deformation is for all the segments. Okay, that is what we call elastic segment, elastically deformable segments as opposed to rigid bodies. That is how we can characterize and understand compliant mechanisms as opposed to rigid body mechanisms. Within compliant mechanisms, we have those that have discrete compliance like these flexural joints, like in this pair of scissors or a forceps, or we can have the distributed compliance that is achieved with elastic segments, which are basically beams here. Okay. Now, kinematic pairs, as we all understand from traditional mechanisms, there are a number of them, the revolute joint, prismatic joint, helical joint and so forth. And these are all lower pairs, meaning here the contact between two bodies are going to be surfaces. But if you look at higher pairs, that can have line or point contact. But what is true about all of these kinematic pairs is that they have specific shapes for these contact surfaces between the two bodies that the joint connects. The kinematic pair, again, it is called a pair because it connects two bodies, and these two bodies should have complementary shapes. If you take a revolute joint, there should be a surface of revolution of any kind. You draw any curve and have a surface of revolution, and you will get this revolute joint. Similarly, if you have prismatic surface, you have prismatic joint or a slider joint. Helical surface, you get helical joint and so forth. Planar surface, you will get 3 degrees of freedom in a plane. That is basically, if you put a block on a flat plane, that block relative to the flat plane will have 3 degrees of freedom. The x motion, y motion, both translations and rotation about the z axis. But then there are specific shapes for all of these things. Okay. Here is a design principle that one of the great designers, Michael French, wrote in his book. Prefer hinges to sliders and flexures to either. What he means is that whenever you can use flexural joints, use them, and your preference for those is above the hinges and sliders. Of course, between hinges and sliders, hinges are better than sliders because hinges or revolute joints will have less friction than sliding joints. Okay. Prefer hinges to sliders and flexures to either. So, what Michael French is telling us here is that go for flexural joints whenever you can. So, here once again the discrete compliance, if you want, here is how you can get. You can take a sheet and mill out a slot such as this. Okay. So, you can take a let us say polypropylene sheet, which by the way is a very good material for making compliant mechanism prototypes. You can take a sheet and it is just a planar machining in milling, you cut out these. What you get are the flexural joints. Okay. That is a discrete compliance. Compliance is here and here and here and here. If you put a screw here and turn this screw to advance it this way, when this moves up, this is going to move like this. It may not be obvious when you look at this picture like this, but let us look at this like that. That is, we have joints that we just indicated, flexural joints. Imagine them to be rigid body joints now or hinges. The orange lines indicate abstraction of the bodies. So, here is one rigid segment, here is another rigid segment, here is a third one, and the fourth one of course is the frame itself. This is discrete compliance. You just have a few flexural joints and it does what you want. In fact, it turns out to be a Chebyshev straight line generating 4-bar linkage. Elastic pairs can be of many different shapes, and here there is no specific shape like it is there for kinematic pairs. So, for single degree of freedom itself, you can have a number of sliding pairs, single degree of freedom, revolute or rotational pairs, single degree of freedom, so many things are there, and 2 degree of freedom, again a number of them are there. They are all different from one another in terms of their shape, but they all do the same thing, meaning 1, 2, 3, 4, 5, 6, all these 6 are going to give you 2 degrees of freedom rotational pair, and all of these encircled ones give you elastic 1 degree of freedom rotational pair, and these are elastic 1 degree of freedom sliding pair. What you need to notice is that there is no specific shape for elastic pairs, unlike it is there for kinematic pairs. Here is a finite element simulation of some of these joints that can be easily done, and we will be looking at some of those a little later in the course. And all of these you can do and then say that they have similar behavior as compared to rigid body joints or kinematic pairs. In fact, there is one called Bendix elastic rotational pair, which has been in use commercially for a long time, which is this one. If you type Bendix in Google, you will find that nice animations. If you look at how it works, it has been commercially a very successful one and has lasted a long time. Some of these elastic pairs can be quite complicated, as you see in the device that are shown here. These are basically 2D translational sliding pairs like an XY stage, but all with one piece. This one, if you apply actuation here, the central platform will move purely in the x direction without any motion in the y direction. Likewise, if you apply in y direction, that will move purely here or not in the x direction. So, it has that decoupled motion between x and y, and rotational stiffness, other stiffness are very high. This particular one looks even more complicated, that has 2 layers of actually metal here, that is a prototype that is made, which has displacement amplification included within this, and have these 2 decoupled xy motions, both translations, and one layer of this is shown here. Take another layer, turn it by 90 degrees, and then attach at the central portion, you get this mechanism. Some of them can be very complicated because their shapes are not anything specific, only the resultant motions you see. This again I emphasize the difference between kinematic pairs and then elastic pairs. If you compare these two, that is distinguishing kinematic pairs, elastic pairs, you have in a kinematic pair ideally, meaning that there is no friction or backlash, you have 0 stiffness along or about the intended axis. Let us say if it is rotation about x axis, you have no stiffness or resistance to move it about x axis, to rotate about x axis or move along x axis, and infinite stiffness about all other axes. If you have one sliding joint like a piston and cylinder, when you move piston in the cylinder, there will not be any resistance, or there will be very little resistance or due to friction or other things maybe, but if there is no friction, it will have no stiffness at all. And if you try to move that in any other direction, you will feel infinite stiffness. That is a characteristic of kinematic pairs. And friction and backlash, of course, will cause deviations from the ideal condition. As opposed to that, elastic pairs, they are more realistic. They have finite but low stiffness along or about the intended axis. If there is a flexure about, let us say, z axis, it will have stiffness but low enough stiffness to rotate about the z axis, and finitely large stiffness about other axis. And there will also be this cross axis errors, that is, if you move about x axis, there may be some movement about y and z axis also, either translations or rotations. So, there will be cross axis. Here the cross axis errors are usually very small or not present at all. Here you have friction and backlash, whereas for compliant mechanisms there is no friction, there is no backlash. But viscoelastic behavior, whether it is made of polymers or metals, can cause deviation. Sometimes the axis itself might drift a little bit, which is not usually present or does not happen in kinematic pairs. We need to understand these two very well as to what kinematic pairs can do, what elastic pairs can do. If you want to look at it mathematically for small displacements, we can put that in this form like force displacement relationship, where u's are displacements, let us say ux, uy, uz, 3 translations, and theta rotation about x axis, phi rotation about y axis, psi rotation about z axis, and corresponding forces for translations and then moments for rotations. So, if you say k u equal to F, k is the stiffness matrix which is multiplying the displacements, which can be generalized, meaning translations and rotations, corresponding forces which again generalized, so forces and moments. So, having this stiffness values kxx, kxy and so forth, you can characterize whether something is a kinematic pair, an elastic pair. Since it is stiffness, if it is let us say translational pair, sliding pair about along x axis, then kxx will be 0 and all these other things will be infinite, because there is high stiffness or resistance about them. Okay. Likewise, if it is the rotational one, k theta will be 0, all others will be infinite. That is how it is in the kinematic pair. Where elastic pair, if you take, if I say rotation about x axis, k theta will be small but not 0, finite but small. Others are not infinite, but they will be finite and very large, and that is how one has to design elastic pairs. If you look at the reverse of it, where I define the inverse of the stiffness matrix as compliance matrix C, then we can talk about this. Well, let us say if I want translation about the z axis, then CZZ, because it is compliance, it has to be very high, all others have to be 0, because the compliance opposite of stiffness. Okay. Again, we can talk about how to design elastic pairs by looking at these values. There will be some target values depending on how much stiffness you want about the intended axis, which should be low stiffness or high compliance, and about other axis high stiffness and low compliance. So, you can look at those things and design. Okay. Now, having looked at that, if you look at this mechanism, this is a distributed compliant mechanism. There are no elastic pairs here. Even if you want to look for them, you do not find, you only find beams that are long, and there are some holes here and there. And how does it work? Again, before I show the mechanism, let us look at the fact that there are no elastic pairs in this. That is a characteristic of distributed compliant mechanism, and this deformation when it moves, as you will see, is uniformly distributed throughout the mechanisms, more or less. It will not be the same everywhere, but entire mechanism is going to be deforming, and you have large displacement here, but small strain. Okay. Of course, when I show the device, you can't see that there is small strain unless you do finite element analysis or some other analysis, but you can see that the deformation is there, but it is causing large rotations and displacements rather than stressing or straining individual parts. And such mechanisms are stronger than those with elastic pairs, because that forceps I showed, if I apply too much load at the flexural joint, it can easily break, whereas when you take a distributed compliant mechanism, it will not. But of course, there is enhanced scope for design, because if you take elastic pairs, you can just imitate a rigid body mechanism, replace a joint with a flexural joint, that is a kinematic pair with an elastic pair. But the moment you go for this concept of distributed compliance, then you can design them in many different ways. So, here is the device that is fixed over here and over here. You can see little screws. This is actually a board, and when I apply force here, it is going to move like that. Looking at this, you can't say that I am actually straining a particular portion a lot. Okay. This is a gripper. So, when you apply force somewhere, two things are coming to grasp something and grip something. After all this, if we want a definition for compliant mechanisms, here it is. A compliant mechanism is one that uses elastic deformation to transmit, or you can put also and if you want, transform force, motion and energy. So, if you have a rigid body linkage here which has these joints, when I press these handles, it will move like this and close the gap. It is a mechanism, because if you put an object there, it will do some work on it. The same thing you can get with a thing that does not have any joints, only you have elastic segments here. This transforms your force that you apply in the handles to somewhere else to do some work, force, motion or even energy. The transform part of it will come to a little later in this lecture. So, I have this device here to show you, where you have this thing there. If it is fixed at the bottom portion, and if I press these handles, it will move down. In fact, if you were to have this device in your hand, if you put your finger over there and do it, you can actually make yourself scream, meaning that it has very good mechanical advantage. With little force, you can generate a lot of force at this point. So, this is the a mechanism that amplifies force. There are other things where you can amplify displacement if you want. So, here is one that amplifies displacement. Let us look at the screen first. So, there are these movies of real prototypes where you are applying a force. It is just a big aluminum arrow that we have made to illustrate. So, you apply a force here, it is moving with a large displacement over there. This is a displacement amplifying mechanism, compliant mechanism. It amplifies, compliant mechanism can amplify forces or motions, and they can change direction and change the dynamics, also change state in some sense. If it is a bistable device, it can have two stable states, it can do that. Let us look at a changing direction mechanism, which is at the bottom here. When we apply force over here to the right, this goes like that. I have a real device that shows here. So, if I apply force, I am pushing this up and down. So, I have to get the hand right. If I am pushing it up and down like this, it goes like that, right. It can change direction. I am vertically pushing up and down, and it goes. You can see how much deformation that it has, right, and how much output it is giving. Okay. And here is another device. This is also a displacement amplifying compliant mechanism, which is fixed over here. This entire piece is fixed, that is screwed onto this board. When I apply force downwards, this thing moves upwards by a large amount, right. This is a displacement amplifying compliant mechanism, and when you hold it in your hand, you would feel that there is large displacement and large rotation, but there is very little strain, and even if you do billion times, this device is not likely to fail. Okay. So, compliant mechanisms can act like transmissions because they transmit force, motion as well as energy. So, if you look at that device that I just showed, changing direction one, it can be put to use, and here one of my students have created a soil moisture sensor without using electrical power. It works by using a material, super absorbent polymer, which swells and basically expands by about 300%. Now, if you put a compliant mechanism over that and do not let it expand as much as it wants to, it will apply force and move this mechanism as I just showed. So, based on that, they are come up with something called Neer-Sameksh. It just as a all mechanical, you just need to put a little bit of moist sand in here in a cartridge, and there is this material, super absorbent material, which absorbs moisture from the soil just like roots of a plant would do, and then based on that, this pointer that is over here would move and indicate 1, 2, 3, 4, 5 levels. Based on that, even somebody who does not read, there is type of soil and type of crop you put in, based on 1, 2, 3, it will instruct them as to how much water they have to put, as you can see in the label close up here. Okay. And all that is done with a simple compliant mechanisms, as this video that is sped up for showing. It takes about 30 minutes for this to do, and you can see that pointer moving. And, let me play it again, so you can focus on the pointer which is here now, and it is moving as there is moisture absorbed and it is trying to expand. Compliant mechanism takes that force. You see, a large mechanism takes that little force generated by an expanding polymer that can move this. That means that you can have little force and generate a lot of motion. Let us look at the transmission part. Transmission part is we already looked at. Now, let us see what transformation it can do, or transduction. Transduction, as many of you would know, is converting one form of energy to another form. That is exactly what this does. Here there are two electrodes. When apply electric potential between them, as you will see what happens. So, it is getting hot, it is also moving. It is a electrothermal actuator. It is an electrothermal actuator, which if I put it in a slightly different form, I get a gripper with embedded actuation. So, here an elastic material which is also electrically conducting, thermally conducting, and if you apply potential difference between 2 points, it is able to generate motion and it is able to generate do the mechanical work as well. It can move just like the device that I showed a few slides ago. Here you are actually transforming electrical energy into thermal energy and then mechanical energy. That is what compliant mechanisms can do. And there are a lot of advantages of compliant mechanisms. If you take a normal stapler, what you see here is a stapler that has only one piece design. So, entire thing can be injection molded as one piece, except this metallic insert also can be put as insert in injection molding. This is as opposed to normal stapler. If you break it apart, there will be many parts. In 1994 when we did it, there were actually 20 parts there, but you can make something that is like uni body or single piece compliant mechanism. And here is another version of that, or this is a windshield wiper mechanism that was done by Sridhar Kota, who is a professor at University of Michigan, where you can have day to day things made of compliant design so that you can get one piece design. There is a company called Flexsys where you can learn more about this and many more designs. And there are many other things that you can do. One of them is the miniaturization, as it will show here. Towards miniaturization, we have normal forceps to which a compliant mechanism is attached. When you close the forceps, you can pick up something. So, the idea is that if you want to, here is an yeast ball. If you want to pick up something small, you do not have to necessarily make things very small. Okay? And here is the idea of that. If you want to make a compliant mechanism that can pick up a single biological cell, biological cells are of the order of animal cells, rather of few microns. Red blood cell, one of the smallest animal cells, is about 5 microns, 7 microns in diameter, and all other cells will be slightly bigger than that, but of the order of microns. If you want to pick that up, you take a bigger compliant mechanism, put in that a little compliant mechanism, small one, whose magnified view is shown here, and here is where the cell would be grasped. And some of the beams here will be very small, they can be as much as 5 microns in width and a couple of few microns along the thickness direction, with which you can hold zebrafish embryo, single cell, biological cells and so forth. Here we have zebrafish embryo. You will see that the gap I showed in the previous slide, and you can actually press. A cell is like a drop, if you will, and you can actually grasp and press on it, and you can do mechanical characterization. And there are many other things that you can do by having these compliant mechanisms that can give you geometric amplification GA, or you can tune their stiffness the way you want. You can go down to the stiffness of single biological cells which have very low stiffness, as well as very high stiffness of many other things as well. We will pause here and continue in the next lecture.